All right, students, welcome to a video lecture for section 2.2, Systems of Linear Equations, Unique Solutions. All right, if you have your notes out and handy, we're going to get started. The learning objectives are listed at the top. We are going to do the first two things today. We're going to write a system of linear equations as an augmented matrix, and we're going to identify whether a matrix is in row reduced form, and this will probably be split up between two videos. All right, what we're going to be talking about is something called the Gauss-Jordan elimination method. And we're using this method to solve systems of linear equations of any size. We've already done systems of equations with two linear equations and two variables, and we're hoping to be able to solve things with systems with more equations and more variables. All right, now the reason we want to do this is it's very adaptable to the computer, and we would like to understand how our computer is solving these systems. This will involve a sequence of operations on a system of linear equations to obtain at each stage an equivalent system. That is, a system having the same solution as the original system. And each time we do a reduction, the new system is simpler, and we can easily read the solution if we can get that to be simple enough. All right, the operations that we can use in this Gauss-Jordan elimination method are, number one, we can interchange any two equations, so we could switch equation 1 and equation 2, we could put them in any order. Number two, we can replace an equation by a non-zero constant multiple of itself. And number three, we can replace an equation by the sum of that equation and a constant multiple of any other equation. All right, so we're going to do this first example in our first video, and you could call this the long way. We're going to be solving this, and we're going to be changing our equations at each step, trying to make them simpler. And you'll see sort of the method as we go through. All right, we've got three equations and three unknowns, and we've got x, y, and z. And the first thing we want to do is try to simplify the very first equation. And if you'll notice, this first equation is 2x plus 4y plus 6z equals 22. If we wanted to simplify that, we could easily multiply equation 1 by a half because all of those coefficients and the constant are even, and that would be simpler. And when we do that, we would get x plus 2y plus 3z equals 11. Now we have a new system of equations. We've changed the first equation, and it seems logical that this equivalent system would have the same solution as the original system. All right, now we want to continue to simplify this, and you might notice that if we wrote down equation 1, which is x plus 2y plus 3z equals 11, and equation 3 right below it, negative x plus y plus 2z equals 2, if you notice, the first two terms are equal and opposite, and if I were to add those equations together, the x would be eliminated, and I would have 3y plus 5z equals 13. So I added those two equations together, and I got a simpler equation. This equation is simpler than any of those three. And we're going to replace equation 3 with this new equation. So I'm going to go down a little bit at the top of the next page. You can see we've got 3y plus 5z equals 13. Now, we also want to do the same thing, we'll come back to that in a minute, with equation 1 and equation 2. But now notice equation 1 has x as the first term, equation 2 has 3x as the second term. If I added these two together, the x's would not drop out unless I changed equation 1. So that's exactly what I'm going to do. I'm going to take negative 3 times equation 1. If I did that, I would have negative 3x minus 6y minus 9z equals negative 33. And then I'll write down equation 2 under it. Positive 3x plus 8y plus 5z equals 27. Add going down. Since I chose that negative 3, now the x terms drop out. I'll have 2y minus 4z equals negative 6. Again, this is a simpler equation than any of those first 3 equations. And so I'm going to place that right here. 2y minus 4z equals negative 6. All right, so now we still have 3 equations. The first equation is simpler, and the second and third equations are even more simplified because they only have 2 variables now instead of 3. And again, this is an equivalent system. It has the same solutions as any of the systems that we've written before, namely the first system. All right, now suppose we repeat this process and we wanted the first term to be x with a 1 in front. Next, we want this second equation, second term, to have a 1 in front of the y instead of 2. And notice we can easily take 1/2 times equation 2, and we're going to put that right here. So half of equation 2 would be y minus 2z equals negative 3. It is simpler. All right. Now once we've done that, take a look at equation 2 and equation 3. We should be able to do some algebra and eliminate the y from equation 2 and equation 3. So equation 2 and equation 3. Equation 3 we know is 3y plus 5z equals 13. Equation 2 has a y in front of it. So let's multiply equation 2 by negative 3. So we would have negative 3y plus 6z equals negative 3 times negative 3 is 9. And I can add those going down and the y's will drop out. And I'll have 11z equals 22. All right. Look at that. We've eliminated the y. I'm going to put that right over here. 11z equals 22. Notice also we could do the same thing with equation 1 and equation 2. We could write down equation 1, which is x plus 2y plus 3z equals 11, and negative 2 times equation 2, so that we would have negative 2y plus 4z equals 6. Notice now the 2y and the negative 2y would drop out. And I'm going to draw a line here and add going down. The x will be here, the y's will drop out, plus 7z equals 17. So we're going to put that right over here in the first equation. X plus 7z equals 17. Okay, great. Now, each of the 3 equations only has 2 variables in the first, 2 variables in the second, 1 variable in the third, and we can simplify equation 3 just by multiplying by 1 over 11. If we did that, we would have z equals 2. I'm going to write that down here on the next line. All right, so we've got z equals 2. So that means we'll still have x plus 7z equals 17, y minus 2z equals negative 3, z equals 2. We want to eliminate z from the first and the second equations. All right, let's do equation 1 and equation 3. We can write down equation 1 minus 7 equation 3. X plus 7z equals 17. Negative 7z equals negative 14. Add going down, x equals 3. All right, x equals 3 goes right there. Now we need to do the same thing with these two equations, equation 2 and equation 3. And let's see, if I write down equation 2, y minus 2z equals negative 3, notice that means I'll have to multiply equation 3 by positive 2. 2z equals 4. Add going down, y equals 1. So I'll put the 1 right there. All right, so I've got this equivalent system, and it has the exact same solution as the original system, and in fact it tells us what the solution is. The x equals 3, the y equals 1, the z equals 2. And we're going to just write that as an ordered triple. It's the point 3, 1, 2. It is the intersection of the three planes described by the three equations in the original system. And we could test those values in the original system to make sure that they satisfy all the points, all the planes, in other words, all the equations.